Good afternoon, everyone. We're going to give it another minute or two, and then we will begin. So thank you all for waiting. All right, it is now 1 p.m. Eastern, so we're going to go ahead and get started. So good afternoon, everyone, depending on where you are joining us from today. On behalf of the Environmental Finance Center Network, welcome to our webinar today on chlorine disinfection and CT calculations for small water systems. My name is Avery Davis from the Syracuse University Environmental Finance Center. And before we begin, we're going to cover a few housekeeping items, and then we'll get started. During the webinar today, everyone will be kept on mute to ensure audio quality. If you have a question, please type it into the GoToWebinar question dialog box anytime throughout the session. We will be saving your questions for a facilitated Q&A session at the end of the presentation. After the webinar, you will receive a follow-up email that includes a link to the recording and other information you may need. You can also download the slides from today, the agenda, and additional exercises related to today's discussion in the Handouts tab in your GoToWebinar control panel. This session has not been submitted for pre-approval of continuing education credits, but eligible attendees will receive a certificate of attendance for their personal record. To receive a certificate for this session, you must attend for the entire duration of the webinar. You must register and attend individually using your real name and unique email address, and we will not accept group viewing credit. Certificates will be sent via email within 30 days of the webinar date, and you can use this document to self-submit for credit if it is available. It is the responsibility of the attendees to verify with their licensing agency what they need to do to receive credit for their attendance. If you have any questions or need assistance, please contact us at smallsystems@syr.edu. Now for a little bit about us. The Environmental Finance Center Network provides training and technical assistance to small public water systems in all U.S. states and territories to help local water systems achieve their goals and stay in compliance with the Safe Drinking Water Act. If your community or utility needs assistance with drinking water system management, please feel free to contact us through our request form, which I will be sharing shortly in the chat. And on that note, I would like to introduce our presenter for today. So welcome Gregory Pearson, who is the Water and Wastewater Systems Trainer at the Great Lakes Environmental Infrastructure Center at Michigan Technological University. So Greg, I'm going to make you a presenter and we can go ahead and get started.
Thank you, Avery. Welcome, everyone. Today's class is, as Avery mentioned, is chlorine disinfection and CT calculations. And you deserve to know a little bit about who's speaking to you. So once again, this is like that. Okay, you deserve to know a little bit about who's speaking to you. And as Avery mentioned, I'm the Water and Wastewater Systems Trainer at the Great Lakes Environmental Finance Center. And that's at Michigan Technological University up in the Upper Peninsula of Michigan. And in my experience with water, I started out as an operator, and I'm currently certified in water treatment, water distribution, and wastewater treatment, and have experience with operating and managing a utility. And also I've been a trainer and technical assistance provider since 2006, and have gotten to interact with hundreds of systems. And so that's kind of the perspective I bring. Also up here, we actually do have flowing liquid water at certain times of the year. The rest of the year, water is often in its solid form up here. The big idea of this training is we're going to bring together the theoretical, mathematical, and operational aspects of chlorine disinfection. So we want to combine those three elements and take away some practical applications. Let's jump right in. But first of all, we'll have our first poll.
So for our first poll, it asks, what type of disinfection does your water system use? And the answer options are no disinfection, sodium hypochlorite, calcium hypochlorite, gas chlorine, or other method. And we're going to leave it up for about 15 more seconds, so make sure you get those answers in. Okay, the poll is closing in 3, 2, 1. Can you see those results, Greg?
I cannot see them on my screen.
All right, so it looks like 13% answered no disinfection, 59% answered sodium hypochlorite, 3% answered calcium hypochlorite, 16% answered gas chlorine, and 9% answered other.
Thank you for participating. The basic layout of this training, we have three parts to the training. The first part is more theoretical. We're going to be looking at dosage and residuals in from the perspective of the chlorine breakpoint curve, looking at concepts like demand, combined chlorine, and free chlorine. In the second part of the training, we're going to actually calculate feed rates for gas chlorine, liquid sodium hypochlorite, and the solid form of chlorine, which is calcium hypochlorite. And in part 3, we're going to look at CT values. CT values mean concentration in milligrams per liter times time in minutes. And we're going to look at those CT values in relation to the log inactivation tables for 4-log virus inactivation and 3-log Giardia inactivation. So looking at the chlorine breakpoint curve. Now, what is this curve? It's basically a graph of the total residual as chlorine is added. So as we add chlorine, what do we measure in terms of total residual? And the concepts we're going to take away from this slide here is, first of all, the dose is the amount of chlorine added to water as a concentration in milligrams per liter, and milligrams per liter is the same as parts per million. So as we see on the x-axis, we're looking at the chlorine concentration going up, or more chlorine being added. Now we're also going to look at the total chlorine residual that we measure as a result of adding this chlorine. We also measure total chlorine residual in milligrams per liter, and that's on the y-axis of the graph. And something happens here at the break point. We begin building free chlorine residual, and generally we think of this chart in 4 distinct segments, and we're going to look at each segment in order here. So overall, we're looking at what is the effect on the total residual as chlorine is added. So let's dive in and take a look. We're going to look at that first segment first. Segment A, as chlorine is initially added, the first little bits of chlorine that are added, no chlorine residual is measured. Well, why is that? Because the chlorine is used up by reducing compounds. So what are reducing compounds? They're compounds that chlorine reacts with, for example, iron and manganese. Chlorine oxidizes iron and manganese, and it's used up, and it does not contribute to total residual. As we go to the second segment in the chlorine curve, we begin to build total chlorine residual. You can see the curve now raising up. We now have measurable total residual, but there's no free residual yet that we can measure. What is happening in this stage? Well, chlorine is reacting with organic compounds that are naturally occurring in the water. So it's forming chloroorganics, which can consist of chloramines, disinfection byproducts, and different types of organic chemicals. So what we have here is combined chlorine. Chlorine that is combined with organic compounds such as chloramines and disinfection byproducts. And chloramines are chemicals that are resulting from chlorine bonding with nitrogen products such as ammonia. Once again, there's no free chlorine at that point. As we add more chlorine, we get to a third stage. And you notice something odd happens to that curve. It was going up, and now it's going back down. Even though you've added more chlorine, the total chlorine that you're measuring is now decreasing. In this point, what's happening is as you add more chlorine concentration, these chloramines are partly destroyed. And so the total residual goes down a little bit. Also, another thing is happening. You notice the green box above it says monochloramine, and the kind of orangish box says dichloramines. The chloramine compounds are actually partly changing form as well. So the monochloramines are partly destroyed and partly converted to dichloramines. So another concept to look at here, when a system is actually using chloramines to disinfect, they're often looking at a ratio of 5:1 chlorine to ammonia, and that is usually very close to the peak of that curve, where you're getting the maximum amount of monochloramines produced. In the fourth stage, we've passed that break point, and we can now begin building some free residual. Free chlorine residual means unreacted chlorine. You notice where that red dot is, that represents the height of the total chlorine residual that we've reached. But notice there, that horizontal line below where it says free available residual, below that line, there's still some combined chlorine. So the total chlorine residual that you measure is going to be a little larger than the free chlorine residual that you have, unless your water were to be completely pure, like distilled water. A couple of concepts in this slide. The chlorine demand are the compounds which either use up or react with chlorine. And the free residual is the unreacted chlorine portion of the residual. And there's that breakpoint line that divides total chlorine residual only and total chlorine that includes free residual. If we were to look at a diagram of what's happening, it would look something like this. Let's consider an example. I'm going to give you two examples where we're going to look at demand in two different ways, depending on what kind of test we're using. In this example, we have a dose of 1.5 milligrams per liter that we're adding to water. And it has a chlorine demand of 0.2 milligrams per liter that's due to reducing compounds. But the total residual that we're measuring is 1.3 milligrams per liter. So let's take a look at this. Notice that that total residual of 1.3 milligrams per liter includes the free chlorine and some combined chlorine. And in the green at the bottom, we're representing that 0.2 milligrams per liter that was used up. So the total chlorine measures the combined and the free, but it cannot measure the reducing compounds that have destroyed, the amount of chlorine that was destroyed by reducing compounds. Now let's look at the same dosage using a free chlorine test in the next slide. You see at the bottom, if we were to write this as an equation, dose equals residual plus demand. We're going to do the same thing with free chlorine now in this slide. Once again, we have a dose of 1.5 milligrams per liter, and we still have that chlorine demand due to reducing compounds of 0.2 at the bottom. But this time, we measure a free chlorine residual of 1.0 milligrams per liter. Our total chlorine demand in this slide is an addition of the combined chlorine plus the chlorine that's used up by reducing compounds. So if we were to write this as an equation, our dose of 1.5 milligrams per liter equals the 1 milligram per liter of free residual that we measure, plus the 0.5 milligram per liter of the total demand. So that should give you a good idea of the relationship between free chlorine, combined chlorine, and reducing compounds, and the total chlorine that includes free plus combined. So if we were to look at the comparison of what's being measured, the chlorine dose includes everything, and the free chlorine test only includes that unreacted chlorine. So let's try to apply what we've learned here. So we look at a water that has a demand of 0.4 milligrams per liter, and our intended free residual is 1.2 milligrams per liter. So we remember from our last slide, we can add residual and demand to get our dosage. So our residual of 1.2 milligrams per liter plus our demand of 0.4 milligrams per liter gives us a dose of 1.6 milligrams per liter. And the key phrase also to look at here in this question is this is total demand. So the total demand is including the chlorine that's destroyed by reducing compounds and that combined chlorine. And if we were to look at this graphically, we see the free chlorine portion here is 1.2 milligrams per liter. And then our total demand is some kind of combination between the combined chlorine and the chlorine destroyed by reducing compounds, which totals 0.4. And that about concludes our conceptual theoretical look at chlorine. And just to clarify, when we're talking about free chlorine and total chlorine, those are concepts for the residual, but they can also be tested depending on the type of reagent that you use. Here we have an option of two reagents on the left-hand side of the screen, either a total DPD, DPD means you're using color, or a free. So basically what we're doing is we're taking a test tube, we're adding reagent to the water, and it will react and produce a pinkish to reddish color, and then that reddish color is interpreted by a colorimeter, which will convert that to a chlorine concentration. Now we're moving on to part 2 of our presentation. That was the theoretical, and now we're going to look at some calculations for gas chlorine, liquid sodium hypochlorite, and solid calcium hypochlorite. And this class moves a little bit fast, I realize, because we're covering a pretty wide swath of information in 1 hour. And a couple things that I would advise is to download the presentation and download the additional resources, but also this presentation will be recorded and you can go over it again if I happen to go a little bit too fast on some of these calculations. First of all, we have the pounds formula for gas chlorine, and it has to be in this form. The flow has to be in the units of million gallons per day, which in million gallons per day, 1 mgd is equivalent to 1 million gallons per day. So it's kind of a shorthand. Instead of having to write 1 million, you can just write the number 1 times milligrams per liter. That's the units for our dose concentration. And then we use the weight of water, which is 8.34 pounds per gallon. So we multiply across that, and that gives us a feed rate of pounds per day. Keep in mind that's a rate. And here we have an image of a 150-pound gas chlorine cylinder. And you notice there's a regulator there that regulates the amount of vacuum that's allowed to draw on that chlorine gas container. The injector or ejector is probably the better term. It's a venturi where the water flowing through that pipe is necked down, so it creates a vacuum. And you can regulate the amount of vacuum that is allowed to pull on that chlorine tank by adjusting that regulator. And then the chlorine feed rate reads out directly in pounds per day. You have a rotometer here, and as you adjust that regulator, a little ball will float up to a particular setting. And so if your target is 20 pounds per day, for example, you would adjust that regulator till that little ball rests directly on the 20 pound per day mark. Let's do an example calculation here. Here's a problem that we're going to solve together. What is the feed rate setting for chlorine gas in pounds per day if the plant flow is 1.2 mgd, million gallons per day, and the required dosage concentration is 1.5 milligrams per liter? So all we have to do is plug those numbers into our pounds formula. We plug 1.2 mgd in for flow, 1.5 milligrams per liter for dosage, and the 8.34 pounds per gallon is a constant. It doesn't change. So we simply multiply across 1.2 times 1.5 times 8.34. It gives us 15 pounds per day. So we would set that rotometer on 15 pounds per day. And I want you to think a little bit about how this applies to the slides we just saw about dosage and residual. Our dosage is 1.5, but the residual that we measure in the water is going to be a little less, isn't it? Because of why? It's because of there's going to be some reducing compounds in the water and possibly some nitrogen compounds that combine. So who knows what depends on the water that you're trying to disinfect. The residual will be a little less unless it was pure ionized water. And remember, this is a feed rate, 15 pounds per day. So you might only run this system for 2 minutes of the day. For example, if you ran it for a full 24 hours, you would actually use 15 pounds. But if you only ran it for 12 hours for the day, you'd end up using half of that, 7.5 pounds of chlorine. You can also use a pie formula. In the Ken Carey books, they call this the Davison Pie Formula. And the way it works is you multiply across the bottom of the chart to solve the top. It's the same formula. It just makes a handy way to grab your data. And it works out to the same equation as the pounds formula. MGD, flow in MGD, times milligram per liter, times 8.34 gives you pounds per day, your feed rate. You can also use this to solve for unknowns on the bottom of the pie chart. And that middle line going across horizontally across that pie chart that I've extended with a dotted line, that can become a dividing line. In this example here, we have our chlorinator, our rotometer is set at 30 pounds per day. So we're feeding it at 30 pounds per day. And we know the plant flow is 2.1 million gallons per day, but we don't actually know the dose of chlorine that we're adding it. I mean, we could measure the residual, but we don't really know the dose. So we need to calculate to figure that out. So let's put our data right into the pie chart. 30 pounds per day is on the top. 2.1 mgd goes into the flow section, and we place the weight of water into the pie chart, but we don't know the dose. And keep in mind that that center line becomes a dividing line. So we just keep that orientation and create an equation where the 30 pounds per day is still on the top like it is in the chart. And on the bottom, we have 2.1 mgd times 8.34 to solve for the dose. So that can become a handy tool, that pie chart. And what we get is a dosage of 1.71. So we might have been measuring a residual of 1.5, for example, but we really didn't know what our dosage was until we did the calculation. Next up is we're going to look at calculating sodium hypochlorite, the liquid form of chlorine. Two things we're going to look at. One, this is going to be calculated in gallons per day instead of pounds per day. So we're going to have to use specific weight to determine the weight of the liquid. Also, it's going to be a different percent. Gas chlorine is 100% strength, whereas sodium hypochlorite is going to be a lesser strength. And we'll talk about that. We'll show how that works in a second here. Here is the equation for calculating the feed rate in gallons per day for sodium hypochlorite. Now notice the top of the equation is the pounds formula. So multiplying across that gives you the pounds of pure chlorine. Then we're going to convert it in two ways, by dividing by the percent strength and dividing by the weight per gallon. So this top part, it calculates the pure chlorine that we need. Well, in order to get that amount of pure chlorine, we're actually going to have a larger amount of material, a higher weight of material, of liquid material. So when we divide by the percent strength, that'll give us the actual weight of this liquid sodium hypochlorite that we need. Then when we divide by the weight per gallon, that will give us the number of gallons. So it's kind of a three-step, but we can do the calculation all at once. There's three things going on. And if I expand that out, the weight per gallon is actually the specific gravity times 8.34. The specific gravity times the weight of water gives you the weight per gallon of any liquid chemical. So if we look at the fully expanded equation, mgd times milligrams per liter times 8.34 divided by the percent strength as a decimal times the specific gravity times 8.34 pounds per gallon. And let's try that out on a problem. And that specific gravity times 8.34 is the weight per gallon because specific gravity is based on water. The specific gravity of water is 1.0. So here's our problem. Calculate the weight of 1 gallon of 12.5% sodium hypochlorite, assuming it has a specific weight of 1.2. So first of all, we need to figure out how much that weighs. So let's look at that. The weight of water multiplied by 1.2. So 1.2 times 8.34 pounds per gallon gives us 10 pounds per gallon. So a gallon of this bleach, this 12.5% sodium hypochlorite with a specific weight of 1.2 actually weighs 10 pounds per gallon. Also consider the percent strength is a percent by weight. So percent strength means 12.5% of the weight is pure chlorine. So we can also conclude if we take 10 pounds and take 12.5% of it, that means we have 1.25 pounds of pure chlorine in every gallon of this sodium hypochlorite. And just to refresh our memory, water has a specific weight of 1.0, and the percent strength means the weight of the chemical that is pure chlorine, the percent weight of the chemical that represents the pure chlorine portion. And if we were to compare the weights of 50 gallons of water and 50 gallons of sodium hypochlorite, we would see that 50 gallons of water weighs 417 pounds, and 50 gallons of this 12.5% bleach would weigh 500 pounds. So there's a significant difference there. And sodium hypochlorite comes in a wide range of strengths. The most common are 5.25% strength and 12.5% strength, but there's a wider range that you can purchase. Also, sometimes people will dilute their chlorine solution to fit their chemical feed pump. And make sure that when you're using the percentage in the equation that you convert it to a percent. In other words, 12.5% is expressed as 0.125. You just move the decimal place over to the left 2 spaces. So here we're going to try one. what is the feed rate for 12.5% sodium hypochlorite with a specific gravity of 1.2 when the plant flow is 0.5 million gallons per day and the dosage is 0.9 milligrams per liter. So we have all the information we need and we can plug it straight in to our formula. Here's our formula once again. And we're going to plug the numbers in for flow, 0.5 mgd times 0.9 milligrams per liter, the dose, times 8.34 on the bottom. You notice we're dividing by the percent strength, that's 0.125. And we're calculating the weight per gallon by using our specific gravity of 1.2 times 8.34. And I've left it in the form where you can see the top of the equation and the bottom of the equation. You see on the top of that equation, it says 3.75 pounds per day. That is the weight of pure chlorine that we're adding. And ultimately, we calculate 3 gallons per day. That's our feed rate for our liquid sodium hypochlorite. We're feeding 3 gallons per day. Now think about this for a second. That 3 gallons, how much does that 3 gallons weigh? Well, each gallon weighs 10 pounds, correct? So we have 30 pounds of sodium hypochlorite in order to deliver 3.75 pounds of pure chlorine. So I hope that gives a kind of a conceptual picture of what we're doing. In every case, we're trying to add enough material to deliver the required amount of chlorine, pure chlorine, or elemental chlorine. Lastly, we'll go to last feed rate we'll look at is for calcium hypochlorite. And this can be a little bit confusing because sometimes we use calcium hypochlorite just to make a liquid solution. But at other times we use it in the form of tablets or can feed it directly with some kind of a erosion type feeder or a tablet feeder. Now, the way this equation works is much like the previous equations. The top of the equation is the pounds formula. Flow in mgd times dose in milligrams per liter times 8.34. That gives us the amount of pure chlorine. But we are actually going to need a little bit more of this chemical because it's not 100% strength. And the calcium hypochlorite is also called high test hypochlorite because it's fairly strong. It generally ranges from 65% to 70% strength. And once again, that's the portion of that chemical that is pure chlorine by weight. So let's try it out. Here we have a calcium hypochlorite powder that is 68% strength. Our plant flow is 347.5 gallons per minute, and the desired dose is 1.2 milligrams per liter. Now I see right away we're going to have to convert that 347.5 gallons a minute to a different unit. And what is that unit? Well, we need it to be in the form of million gallons per day. So let's see, we'll just use this problem to show that conversion. So first of all, we're going to convert the flow to mgd. How we do that, we take that 347.2 gallons per minute and we times it by 1,440 minutes in a day. What that will give us is, instead of gallons per minute, on the top we'll have gallons per day, because that every minute we're getting 347. The second minute we get another 347. So after we look at what happens in an entire day, we get gallons per day. Then we convert it to mgd by dividing by a million. 1 million gallons is the same as 1 mg. So we take it and times it by 1440 and divide by 1 million. So we find out that this flow is actually 0.5 mgd. And now we have all the information we need to plug into our equation. So remember, our equation was flow times dose times weight of water divided by the percent strength. When we put those numbers in, here's what it looks like. 0.5 mgd times 1.2 milligrams per liter, that was our dose, times 8.34. Then we divide by 0.68. Remember, we take that percent strength and move the decimal place over 2. And I've left the top and the bottom still there for the equation. You notice there's 5 pounds per day on the top. That's the amount of pure chlorine that we're trying to deliver. And we divide that by 0.68 and we get our result 7.36 pounds per day. So we need to feed 7.36 pounds per day of calcium hypochlorite in order to deliver that 5 pounds per day of pure chlorine. In the third section here, section 3, we're going to be looking at CT values now. CT, once again, that simply means the concentration in milligrams per liter times the time in minutes. And we're going to be looking at these factors. First of all, looking at what they call baffling factors for tanks, and that's going to affect the contact time. When you have some short circuiting, you get less credit for the tank volume. And we're going to be looking also at the log4 inactivation tables for viruses and the log3 inactivation tables for Giardia, and seeing how we can determine the required CT value that we need to attain and comparing that to our actual CT values. And now, before we launch into that, we are going to have poll number 2.
For our second poll, it asks, is your system required to achieve 4-log inactivation of viruses? And the answer options are yes, no, not sure, or not applicable to me. Looks like about 70% have responded. So we're going to give it about 15 more seconds. Okay, the poll is closing in 3, 2, 1. So it looks like 29% answered yes, 14% answered no, 16% not sure, and 42% not applicable. Sorry.
Thank you for doing that. I can see that you're a good group that stays engaged. I wish we had the ability to talk to each other, but can you imagine what would happen if all 300 of us started talking at once? All right, we're going to jump right in to our first concept, which is baffling. And these numbers that you're seeing here, the 0.1 all the way down to 1, describe different orientations and types of tanks or volumes that affect the contact between water and chlorine. In the top, we have all the way from an unbaffled tank, there's no baffles, which we would only get credit for 1/10 of the volume because there's a chance of short circuiting. And that, as the slide states, the baffling factor, it indicates the degree to which the tank or volume is protected against short circuiting. As we go all the way down to the bottom, where it says the baffling factor is 1.0, that is in relationship to a pipe, which is considered to be plug flow, where you get full credit for that volume. And we'll look at a couple of these individually. Here is a diagram of an unbaffled tank. You see that water entering could potentially make its way over to the exit of the tank before it attains its full theoretical detention time. So there's a potential for short circuiting. So we only, if this was a 10,000 gallon tank, we would only get credit for 1,000 gallons. Why we're doing this, it's going to affect our contact time. Remember, CT value is concentration times time, and that time is time in minutes of the effective detention time. And we get that by looking at the baffling factor of the tanks or the volumes. So in this case, we would take the tank volume and multiply it by 0.1 to get our effective volume. Here's a little bit better situation where we have baffles in the tank that direct the flow. It creates a serpentine action and directs the flow. It reduces those initial velocity vectors of the of the incoming water, and so it has less of an opportunity to go straight from the inlet to the outlet. So generally, these will generally be given a credit of 0.5 to 0.7. And of course, you would work with your primacy agency to determine this. So in this case, if you had a 0.7 baffling factor, you would take the tank volume and divide it and multiply it, by 0.7 to get your effective volume. So if we had a 10,000 gallon tank, 10,000 times 0.7, we'd get credit for 7,000 gallons. And then all the way down to the bottom of that original list was the pipeline. Plug flow is considered a perfect flow. So there's no opportunity for short circuiting. That's the consideration here. So the pipe volume equals the effective volume. Now we use these baffling factors to calculate effective detention time. Theoretical detention time, it assumes that there's no short circuiting. We just have the time equals the volume divided by the flow. So the volume in gallons divided by the flow in gallons per minute. Gallons would cancel and you'd have only minutes left. But the effective detention time is what we're going to use for our CT values. We're going to take into consideration the baffling factor. So we're going to take the volume of that vessel, multiply it by the baffling factor, and then divide by the flow. When you're using this equation, the one thing you want to make sure is that the units on the top match the units on the bottom. For example, volume in gallons and flow in gallons per minute. If you use cubic feet, for example, you'd want to have cubic feet on the top and the bottom, or liters, or whatever unit you use. They just have to match. So let's do an example. Let's look at the effective detention time of a tank. It has a volume of 75,000 gallons, and the baffling factor is 0.5. So we're getting half credit for this tank. And the flow through the tank is 500 gallons a minute. So let's set up our detention time equation. We have 75,000 gallons times that baffling factor of 0.5. Then we divide it by 500 gallons per minute, and we get 75 minutes. So in that CT equation, concentration times time, our time is going to be the 75 minutes. Now, just to compare, the theoretical detention time would have been 150 minutes. So we're getting credit for only half of that tank, but it's more realistic because of the potential for short circuiting. Now, also another factor of why we're doing this is disinfection includes destruction of some organisms like bacteria, but for viruses and protozoa like Giardia, it only inactivates them, makes them unable to reproduce or infect. It doesn't necessarily destroy them. So the effectiveness of chlorine disinfection, it depends primarily on the concentration, the residual, and also on the contact time. But there are other factors such as water temperature and pH. So when we look at the tables, we're gonna look at some tables, you'll see how pH and temperature is handled. Temperature affects disinfection because as it's colder, any chemical reaction proceeds more slowly. So chlorine is less effective at colder temperatures. And we'll look at a slide here in a second that shows why pH affects disinfection. But first of all, let's look at a CT value. This table here shows 3 equivalent CT values, concentration times time. And the first one on the top, 2 milligrams per liter concentration times a contact time of 50 minutes gives us 100 milligram minute per liter. It's kind of a strange unit, but notice we're multiplying milligram per liter times minute. So that's how it's usually represented. If I zoom down to the bottom, 1 milligram per liter, a lower concentration, but a longer time, times 100 minutes also equals 100 milligram minute per liter. So you can kind of see already just from that graph that you can manipulate the CT value by or increase it by raising the chlorine residual. You can increase the time with a larger tank or more pipe volume, or by possibly adding some tank baffling to improve the effective volume. And another thing is adding disinfection segments. If we get time, I have a couple of extra slides that we can look at if we have time, but that information is also in your additional materials handouts. So let's try this. Let's look at a log 4 log inactivation table for viruses with chlorine. And you see it has a table for temperature, and then it has two columns for different pH levels. And what we're going to basically do is match the temperature and the pH of your water. So here's an example. Our pH is 7.5 for our water source, and our temperature is 16 degrees Celsius. So we would use the next cooler temperature, which is 15, and then we would choose that pH 6 through 9 column, because our pH is 7.5, and then we would realize that our required CT value for log 4 inactivation in this example is 4. Okay? So that's how we would use the table. That shows us what we're trying to achieve. Now, why does pH affect disinfection? It has to do with how free chlorine exists in the water. It depends on the pH. Free chlorine residual can exist as hypochlorous acid, which is the more effective form of chlorine. It has higher oxidation potential, or it can exist as hypochlorite ion, and that depends on pH. Now, for example, let me show you at a pH of 7 here. At a pH of 7, 80% of the free chlorine residual exists as hypochlorous acid, and 20% exist as hypochlorite ion. So that's a fairly effective combination. If we were to go all the way to 9.5 or 10 pH, you see that near 100% of free chlorine would exist as the weaker form, the hypochlorite ion. So the higher your pH, the weaker your free chlorine residual, or the less effective your chlorine residual. If you went toward the lower pH, it would become a greater quantity of hypochlorous acid and more effective. We'll walk through a problem here for 4-log virus inactivation. So we have a small groundwater system, and it maintains a minimum free chlorine residual of 0.8 milligrams per liter. And we have this 3,500 gallon tank that we're using for chlorine contact time. It has a baffling factor of 0.3, and the flow through the tank is 200 gallons per minute. So the first thing we're going to do is determine what is required. So we look at the table, and we're going to see what do we need. Well, it's very similar to the last. It's the same result as the last example we did. We have a temperature of 15 and a pH of 7. So once again, we have to achieve a CT value of 4 in this case. So let's, in the next slide, let's look at what our actual CT value that we're attaining is. And how are we going to do that? Well, we're going to look at the volume, the effective volume of the tank, and divide by the flow, remember, to get our contact time. And then we're going to multiply that by the residual. So let's do that. First of all, step 2, after we've determined the required CT value, we're going to determine the effective contact time. So we take our 3,500 gallon tank and multiply it by 0.3, which is our baffling factor, and divide it by the flow of 200 gallons a minute. So our contact time, our effective contact time, is 5.25 minutes. So that's the T of our CT value. What is the C? It's that 0.8 milligram per liter residual. So let's plug that in. 0.8 milligram per liter times 5.25 minutes gives us 4.2 milligram minute liter per liter. So it looks like we've just kind of barely scraped by there, but we are meeting log 4 log virus inactivation, just barely, but we're meeting it. Now, if we were going to look at 3-log inactivation of Giardia, you'll notice it's a little more difficult and it's done a little bit differently. In this case, for Giardia, your tables are going to be categorized by the temperature. You see, this is a table that is for water that's at 15 degrees Celsius. So the tables are usually for 5 degrees, for 10 degrees, for 15 degrees, for 20 degrees, and so on. So we would use this table if our water was in that temperature range. And you notice the columns are organized by pH, and we're looking for 3-log inactivation. Also, another factor we have to consider with Giardia tables is your minimum chlorine concentration. So let's try an example here. So what we're going to do, we're going to find the table for your water temperature, and we're going to use our maximum pH and our minimum free chlorine residual to find what's required. So in this case, our example is we have a maximum temperature of 16 degrees Celsius. So we're going to use the next lower, which is the table we have. And we're going to locate our column where it has the pH of 7, and we're going to find where it has 3-log inactivation. And we're going to line that up with our residual of 0.8 milligram per liter. So there is our line for our 0.8 milligram per liter. And here is our line for a 7 pH and 3-log inactivation. So we can see that we want to attain a CT value of 73. And I think we barely have enough time. I figured if I got to this point, by this time I would show you one additional example that gives you a little more feel. This next example I'm going to show you is, so I'm going to skip over a couple slides, please forgive me. And I'm going to show you an example that's in your additional handouts. And we're going to walk through a little bit more detailed application for CD values for Giardia. Okay, so I'm going to, well, let's go ahead and do our poll now too. Poll number 3, I'll let Avery bring that up.
Yeah, so for our final poll, it asks, what other type of disinfection related training would you most like to attend in the future? And the options are more feed and dosing calculations, more in-depth coverage of CT calculations, prevention of disinfection byproducts, alternative disinfection technologies such as ozone or UV, and chlorine chemistry. And I'm going to go ahead and not share the results for this poll, just use them for our team, but I appreciate you all responding. And I'll close the poll in 3, 2, 1. All right.
Thank you for responding to that. And I'll come back to those slides in a second. But this problem I'm going to show you, it's problem 11 in your additional handouts. But I wanted to take some time and show you this. Now this is a system, it's a little bit more complex, this problem. Not super complex, but just a little bit more detail here. We're treating a flow of 1,200 gallons per minute, and then we're dosing our water just before it enters a 50,000 gallon clear well. It has a baffling factor of 0.7, and then it travels through a 1/4 mile of 10-inch pipe. So right away, we have a 50,000 gallon volume that has a baffling factor of 7. That's adding some contact time. Then that additional 1/4 mile of pipe is adding some additional contact time. So we need to add those 2 times together. The minimum water temperature is 15. That tells us what table we're going to use. The maximum pH is 7, so we know we're going to use that pH 7 column that we just looked at. And the minimum free chlorine residual is 1.2. So we're going to determine, does this system have sufficient contact time to achieve 3-log inactivation? So let's walk through it. Here's a diagram of the system. You see the influent coming in. It's entering the clear well. It's baffled. 50,000 gallons. Then it goes to a 1/4 mile of 10-inch main before it reaches the first customer. So first of all, we'll look at what is the required CT value. So we have our excuse me, our 15-degree Celsius table up here, and we are going to line up our 1.2 milligrams per liter with our 3-log inactivation at 7 pH, and we see we want to attain a minimum CT value of 76. So what we're going to have to do next is look at our contact time and our chlorine concentration and see if it's sufficient to meet this. So let's do that in the next slide. So the total contact time includes the clear well. We take that 50,000 gallons and multiply it by the baffling factor of 0.7, and then we divide that by 1,200 gallons a minute. So we get, in the clear well, we have 29.17 effective minutes for our effective contact time, 29.17 minutes. In our main, we get another 4.48 minutes. And let me show you how we are calculating that 10-inch main. We have a 1/4 mile of main, so we took 5,280 feet and divided it by 4 to get the length of that main. So 1,320 feet in length. And then we converted that diameter to feet. We took 10 inches divided by 12 inches. So instead of putting 10 inches in the equation, we're going to put 0.833 feet. So what we have in the equation is diameter times 0.785. We could also have used pi r squared, but we then multiply it by the length, and then we convert cubic feet to gallons by that factor 7.48 gallons per cubic foot. So we get that water main is 5,378.2 gallons. We divide that also by the 1,200 gallons per minute of flow, and that adds an additional 4.48 minutes. And remember, there's no baffling factor that limits that. So our total contact time is 33, when we add those two up, 33.65 minutes of contact time. And if we multiply that by our residual, 1.2, we only get 40.38 milligrams minute per liter. So that doesn't meet our CT value. So what could we do? Well, we have some different options. We could increase the dosage, add some additional volume, improve the baffling of our tank possibly, and possibly add additional disinfection segments. I'm not going to cover the disinfection segments, but there's a little information on that in your additional handouts. But I will show you the solution using an increased dosage, and then I'm going to stop for the day and show you the final slides, and we'll take some questions. So we find out that if we increase the residual that we are attaining all the way up to 2.8, that gives us our 33.65 minutes we calculated times 2.8. It gives us a CT value of 94.22. And the chlorine concentration that you're using actually changes the CT value that you required. So it's kind of a moving target. So in this case, when we look at 2.8 and we line that up with the 3-log removal, we are required to have a minimum of 89. So with this increased level, we see that the CT value that we're attaining of 94.22 is higher than the required 89 milligram minute per liter. Therefore, we've achieved compliance. And so I'm going to show you a slide here with some reference materials, and these are in your presentation. The first 4 are documents that I recommend that you download them, save them as PDFs, or print them out. Good reference materials for your library. Number 5 is a little reminder that all of these things we're teaching today are dependent on your local primacy agency, because they're the agency that's going to be helping you to determine the baffling factors, the volume credit for your different tanks, and supplying you with the actual tables that you'll need for your state. And lastly, number 6, we have other resources are the handouts, the slides, and the recorded session of this presentation. So I want to thank you for attending, and I'm going to turn it back over to Avery. I used up a little bit more time than I wanted, but please bring any questions that you have.
Yeah, thank you so much, Greg. So we do have some questions coming in. We'll probably only have enough time to get to a couple of them, but we will follow up with you after the webinar if we did not answer your question. So the first one is, does the breakpoint curve look similar for both groundwater and surface water, or are there notable differences?
Yeah, surface water has much more likelihood to have ammonia, and groundwater will have a greater likelihood to have things like iron and manganese. So there'll be slight differences. In groundwater, you might not have very much combined chlorine, a smaller amount.
Great, thank you for answering that. Another question they asked, can demand increase with a higher initial dose? This one came in pretty early in the presentation, I believe.
I don't think so. There could be an effect there where you have a greater amount of oxidation happening all at once, but the demand is really, it's really how much, what is the concentration of the reducing compounds that are in the water. And for groundwater, that will be pretty stable over time. For surface water, that can change from hour to hour, but I can't see any reason why it would change depending on the dose. It more has to do with the constituents in the water.
Okay, and I think there's a couple more questions. We'll probably only get to one. And there'll be a couple to follow up with, but for the final question, they asked, can you describe how operators would determine the chlorine demand?
How would you determine the demand? You'd have to do a calculation to know exactly what your dose is, and then you would compare the dose to the measured residual. That would give you the total demand. If you also compared your free residual test to your total residual test, the difference between the two is your combined chlorine. So take a free, take a total, and calculate your dose using your feed.
All right, thank you so much. So like I said, we'll have a couple questions to follow up with. So if your question didn't get answered, then be on the lookout for that. I would like to extend a big thanks to Greg for sharing his expertise with us today. And following this webinar, you will all receive a follow-up email with the slides, the additional exercises from today, and the recording. We also ask that you complete the webinar evaluation following this webinar so you can let us know your thoughts on today's session. And yeah, that's all I have. So Greg, do you have any last words for the audience today?
I just want to thank everyone for attending, and please send your questions my way, and I'd be happy to help with those.
Great, thank you so much, and I hope everyone has a wonderful rest of their day.